Right, we've got a simple electrochemical cell there, and we're using it to light up this light bulb we've got here. Okay, here's a light bulb. Right, we've talked about this in previous videos, this particular setup. So we've got zinc on the left, and we've got copper and copper rod and copper sulfate solution on the right. Right, let's see what's going to happen. We let the current flow. Well, the copper one is the most positive. This one is the most positive. So that is best at taking in electrons. It's going to suck electrons in. So that means that one's going to go forwards. And it means that this is the most negative, and this is best at pushing away electrons. That's going to go backwards. So the cell reaction will be, of course, it will be Zn plus Cu2 plus goes to Cu and Zn2 plus. And the electrons are going to be pushed this way around the circuit. Okay. Now, eventually, all of the copper ions will be used up, and the cell will go flat. The battery, you'd say the battery was flat. Battery is really a collection of cells, but let's not worry too much about that. So it would go flat, and then what you'd have to do then, if you wanted to use it again, you'd have to recharge it. So to recharge it, what you do is you'd have to get rid of the little light bulb or whatever you've got there, and you have to connect it to a power supply. And you'd have to make sure that was right. This was negative, and this was positive, and your power supply. So this would push the electrons the way round they don't want to go. They'd have to make them go backwards. Now, can you see that? Okay, and the electrons will be sucked up from the copper there. Okay, and the way they don't want to go. And of course, what that would do, it would make this reaction go backwards. Okay, so when you recharge a battery or a cell, all you do is you connect the voltage to push the electrons the way they don't want to go, so they go the opposite way to the cell reaction. And that's what you do every time you plug in your mobile phone and charge it up. Okay, so that's what a practical electrochemical cell is. Now, of course, this would be very impractical because you have to go around with 2 beakers of zinc solution and copper sulfate. It wouldn't give you a very big voltage and so on. But that is the basic principle. Right, now, and we recharge that by pushing the electrons the way around they don't want to go. Now, let's have a look at a real cell, okay? One that is used, and this, we need to know about this. It's on the example. It's called the hydrogen fuel cell. Okay, so we'll have a look at what the hydrogen fuel cell is all about here. All right, here it is. Okay, so now the reason why it's called a fuel cell is because you don't recharge it by pushing the electrons the way round they don't want to go. You recharge it by just continually providing it with fuel, and the fuel is the oxygen and the hydrogen. So as long as you keep providing them, they won't run out, and they will carry on producing a voltage forever as long as you keep providing the fuel. That's what's called a fuel cell. So what we've got an alkaline solution in there in the middle, and we've got 2 electrodes here. Okay, and they are made out of a porous material. Right, that's porous to gases, so the hydrogen and the oxygen can get through it, but not porous to water, so that the sodium hydroxide solution doesn't leak out. And they're coated with platinum because that's a good conductor. Also, it's a catalytic surface for the reactions to occur on. Now, I've got a load connected there. I just put a little light bulb in there, so that's going to be drawing current. Let's see what the cell reaction is going to be then. So here's our 2 half equations. Right, this is the most positive one. So this one is going to be best at taking in electrons. So that's going to push that one forwards. And this is the most negative, 0 hydrogen. Oh, actually, that's the wrong version of the hydrogen one. I'm just going to change that because it's under alkaline conditions. So the actual, it's hydrogen again. It is 2H2O plus 2 electrons is going to give us 2 hydroxide ions, hydrogen, and that isn't that as we that the voltage for that is minus 0.83 volts, and actually the voltage for that one isn't that either, sorry about that. That is plus 0.4 volts. Plus 0.4 volts. Okay, so that's what's going to be happening. So that one's the most positive, this is the most negative. That's going to go backwards, top one's going to go forwards. So if we write down the full equation for that, let's do that. Now we're going to have to multiply this one by 2, because this one is only 2 electrons and that one is 4 electrons. So we're going to get, full equation will be 2H2 plus 4OH minus. And this one's going to go forwards. It's going to be plus O2 plus 2H2O. And that is going to give us, the products are 2H2O on that side. So it's going to be 4H2O because we've got to multiply it by 2, haven't we? Sorry. 4H2O. And the products on this side are going to be 4OH minus. Now there's going to be some things we can cancel out there, aren't there? So we can get rid of those 4OH minus on both sides of the equation. We've got 2 waters then 4 there, so that means we can get rid of those and turn that into a 2. So I'll just write that out again. What do we get? 2H2 plus O2 goes to 2H2O, which is a very familiar equation to us. Now here we are making this reaction occur in a very controlled manner in the cell. Yeah. Now if you get hydrogen and oxygen and light them, they'll explode, won't they? And you'll get lots of energy out. It's very exothermic. But if you just light hydrogen and oxygen, it's quite wasteful. All the energy comes out as heat, which isn't that useful. In this hydrogen fuel cell, the energy of this reaction is used to generate a voltage and generate electrical current. So that is basically what a hydrogen fuel cell is. Let's just draw a cell diagram for that, shall we? So we want our, let's just see which way the electron's going to go in this as well. Well, you can see, look, the electrons are being given out by the hydrogen side here, can you see? And the electrons are being taken in by the oxygen side. So we're going to have our electrons, when the current flows, they'll go from the hydrogen. Yeah. So this is the negative electrode going down into the positive. Let's draw a cell diagram. So we usually put, we always, convention, we put the most positive one on the right. So the positive one is the oxygen, the plus 0.4 volts. So we're going to have oxidized species next to the salt bridge, O2. We're going to put H2, and the reduced form is the OH minus. Okay, we're going to say they're both in aqueous solution. So I'm actually really, let's have the oxygen is really a gas, isn't it? So it's a phase change. And then we will need platinum to make that work. So we need PT there. The left-hand side electrode, well, we've got the oxidized form is here is H2O, isn't it? So we want H2O next to the salt bridge. And the reduced form is hydrogen gas, that's a gas, so phase change, H2, and we'll need platinum there as well. So this is the hydrogen fuel cell, and that's when you're running it under alkaline conditions, okay? Now you may think, why do you need to have it alkaline? Because look at the overall reaction there. It's just hydrogen reacting with oxygen going to water. So why do you have to have NaOH solution here? Why can't we just have water? Well, the reason for that is because water it contains a few ions, of course, it's partially ionized, but it's got a very low ion concentration. So that means that the resistance of the solution would be very high, and you'd have, if you do physics, the cell would have a very large internal resistance, which is not not desirable. So if you're doing alkaline conditions, you get the same reaction occurring, but you get you've got a lot of higher ion concentration in the solution here, so the internal resistance is slower. Right, now you can also operate this under acid conditions, and I'll just draw the equations for acid conditions. The exam board do specify they only want it under alkaline conditions, but let's write it down for acid conditions. So the two half equations would be O2 plus 4H plus 4E minus goes to 2H2O, and the electrode value for that, the E value for that is plus 1.23 volts. And the acidic one would be, you'd have 2H plus and 2E minus, and that's H2 there, and obviously the E value for that's going to be 0 by definition. Okay, which one would go forwards? The most positive is this one. That would go forwards. This is most negative. That one would go backwards. Let's write the cell equation. Well, we'd have to multiply this equation by 2 because this is 2 electrons and that's 4. Let's do that. What would you get? The overall reaction would be, you'd have 2H2 plus on this side, O2 and 4H plus, and it would go to 2H2O and 4H plus. What can we cancel out on both sides of the equation? Well, we can cancel out that, and look at the reaction you're getting. It's exactly the same as you got under alkaline conditions as well. All right, let's look at E cell for that. What would the E cell value for acid be? It would be E right minus E left, which would be 1.23 minus 0, which is equal to plus 1.23 volts. Right, let's work out the E cell for the alkaline conditions. What's that going to be? E cell for alkaline? Well, that is going to be E cell for alkaline conditions. Well, look at the values we've got there. We've got E right minus E left. E right, the positive one, plus 0.4, minus the left one, minus 0.83. Well, that is equal to plus 1.23 volts, which is exactly the same. That's the alkaline. It's exactly the same as the value we got with the acid conditions. Okay, look, it's the same. And what else is the same? Well, the reaction equation is exactly the same in both cases as well. And so it's hardly surprising that they have the same E value. Incidentally, you don't need to know for AQA, but delta G is mathematically related to E cell for a reaction. Well, delta G is obviously going to be the same for both things, isn't it? Because it's the same reaction, hydrogen reacting with oxygen there under alkaline conditions, hydrogen reacting with oxygen under acid conditions here. So the same reaction, the same delta G value, so therefore the same E cell value.